Good morning, everybody. What we'd like to do today is justify the need for using or developing high temperature gas cooled reactors that we mentioned last time. The existing generation of nuclear power plants, the pressurized water reactor and the boiling water reactor, use light water. And we suggested that first, their efficiency is low, maybe 1/3 or 33%, as well as their inability to reach high temperatures. They operate at a temperature of 350 degrees Celsius. If we design new systems that can operate at the level of the 900 degrees Celsius, we increase the efficiency to double what we have today, maybe to 50%, as well as we'll be able to generate high temperatures that lend themselves to the dissociation of water through the electrolysis and heat combined effects into hydrogen. And hydrogen would be used in that case with a new type of an engine, the fuel cell, for a future transportation system. So I'll first have to make the case for the need for going into a hydrogen type of an economy. So in that case, I go to our course on energy storage systems. You can access it and suggest that new developments are being made in the field of electrical vehicles. And let me go to the beginning of the chapter here, and you can access it on the portal for the course of low energy storage systems. And you'll see that electrical vehicles today, the Tesla and the BMW, as well as General Motors, use batteries with a common venture or a joint venture between the Tesla company and Panasonic from Japan. This is the Geiger factory, Panasonic Tesla manufacturing facility. So this is a system that uses energy stored not in gasoline, but in chemical batteries using lithium-ion technology. We all hear about the Tesla particles. It uses electricity. Unfortunately, it is advocated as being using renewables as electricity, but in fact, that electricity is 40%, at least in the United States, coming out from coal. So it's we are using what's called point source pollution, where the coal is released at the coal power stations. Until the day that we use primarily electricity to be stored in the batteries from renewables, wind and solar, as well as nuclear energy, there is no clear advantage in terms of the environment in general. This shows us the batteries at the bottom of those cars. There is an alternative, and the battery technology is quite a very highly developing type of technology. Notice that all these types of batteries depend on the use of lithium. This is the NCA type of battery using lithium. LCO battery uses lithium, LMO using lithium, NMC battery uses lithium. But they use also other strategic resources like cobalt, nickel, manganese, and some aluminum. The cobalt and nickel in particular are resources that are some kind of strategic, and there is a problem with them. Well, let's go quickly and see what is the breakthrough that's happening. You are welcome to read that chapter on your own, but there is a competition from the chemical lithium-ion batteries energy storage with the use of hydrogen coming in from water, obviously, and using it in a fuel cell. And the competition here appears with a design from a Toyota vehicle, electrical. It is electrical still because it stores the hydrogen in those tanks right here. And that hydrogen that is stored there, it's compressed hydrogen. There are other ways you can use cryogenic hydrogen and even solid state hydrogen. But that hydrogen is used in the new type of an engine that we call the fuel cell. As hydrogen is associated with any form of energy, including nuclear, solar, wind, whatever, it is recombined in the fuel cell back into water. The hydrogen combines with oxygen from the air, and it is recombined as non-polluting water. So that is a competition there, but there is a huge advantage of for using hydrogen in that case. And this is shown here in that diagram, comparing the lithium-ion batteries that we use in the electrical vehicles like the Teslas in terms of the energy, specific energy that those batteries can store. They can store 278 watt-hour. Watt is a unit of power. Hour time, watt-hour becomes energy per kilogram of the material that you have in your battery. If you use hydrogen, look at how much would be the specific energy in that case. It rises to 40,000 watt-hour per kilogram. So in that case, you could see immediately that hydrogen stores a much larger amount per unit mass of the storage medium than lithium-ion batteries. Hence, Toyota is developing in that case primarily trucks for this type of a use. So just in case, this is a comparison between the vehicle weight that uses hydrogen fuel cells. Notice how much the weight is reduced compared for a large range. So it's 400 miles. You could see that lithium-ion batteries, electrical vehicles need much larger batteries to be able to make long distance travel. And if you have trucks, it goes without saying that you need first a large amount of energy stored, in that case in the hydrogen, as well as long distance travel. So it is the use of hydrogen in a future transportation system is definitely very competitive with the use of just lithium-ion batteries. And we'll see a very healthy competition between our Tesla here in the United States, and you could see here, actually passenger cars too are being manufactured by Toyota. So Toyota and Tesla are going to be great competitors with some other smaller companies on the fringe in China, in Germany, and in other parts of the world. All right, so here we are going to try to justify today how we can build, in that case, a hydrogen-based transportation system based, in that case, not on the existing light water reactors, but the competition to light water reactors, and that would be the high temperature gas cooled reactor. So when we start building a new generation of nuclear reactors, we have to take that very seriously into consideration. The chapter that deals with this is going to be under the nuclear applications part 10 here, and under energy hydrogenation and decarbonization. Energy hydrogenation, turning our energy system towards hydrogen rather than carbon, has been a dream, even in science fiction. In 1870, Jules Verne, the science fiction French author, wrote in his book, The Mysterious Island, about the use of water. In that case, he thought about hydrogen and oxygen in the water. Jules Verne, as you know, wrote the book on the 10,000 Leagues Under the Sea, which described the Nautilus submarine using, in fact, in his view, nuclear energy. He also wrote a book about a trip to the moon, sending scientists in a bullet from a cannon into the moon. But if you read the quote here, I'll read part of it, quote, and at what will they burn instead of coal? Water, replied Harding. Water, cried Pencroft. Water as fuel for steamers and engines. Water to heat water, yes, but water decomposes into its primitive elements, replied Cyrus Harding, and decomposed doubtless by electricity, which will then have become a powerful and manageable force for all great discoveries by some inexplicable laws, appear to agree and become complete at the same time. He was right to a certain extent, because yes, we can use hydrogen in water, in that case, to run our future transportation system using fuel cells rather than the internal combustion engine, the ICE. And even more that hasn't been thought about by Mr. Jules Verne here, in that we know that water in the oceans contains deuterium, and deuteriums can become a fusion fuel. So in the future, we may be using indeed what Jules Verne considered as the energy source of the future, water in that case. Long before us humans, nature has discovered the wonderful uses of water, and we are a water planet. We wouldn't have life on Earth without water. In plants, they combine water to CO2 in the atmosphere through the process of photosynthesis, releasing the oxygen that we breathe, and generating sugar, C sub 6, H sub 12, O6. For us as humans, we are trying to find another use of water, decomposing it into hydrogen and oxygen. Hydrogen becomes, in that case, a battery or an energy storage medium. It is not that we cannot use hydrogen in an internal combustion engine. We can, but the fuel cell, as I'll show you in a moment, would be a more efficient type of an engine. It is a spin-off of the space program, because NASA used hydrogen and oxygen as fuel for rockets. And in that case, recombining it can provide now not just fuel for rockets, but water for future astronauts. In fact, an internal combustion engine using hydrogen has been developed by BMW in Germany. They call it the Hydrogen 7 car, and they gave it as a gift to, at the time, the governor of California, Arnold Schwarzenegger. But what we are really considering for a future transportation system is the use of the fuel cell. So let's describe what is the fuel cell and why it is that we need high temperature gas-cooled reactors for that purpose. In terms of energies use in general, it is clear that we are tending in our civilization to go to higher and higher specific energy of the from the environment. In that case, we started with wood. It has a very low specific energy. Specific energy means energy that's in megajoule or millions of joules per kilogram of energy. Wood has 10 megajoule per kilogram of specific energy. And it started the Industrial Revolution, burning wood to produce steam, boiling water in that case again, to produce steam. This Industrial Revolution started in England, and they ended up denuding the whole forests and areas of England out of wood. And at some point, they found themselves switching to another form of energy, coal. Coal has 3 times the specific energy of wood. Then the petroleum as a liquid superior to coal in terms of handling is even higher. So petroleum was adopted. And the adoption for our civilization is simply unavoidable. The highest types of specific energy is in natural uranium, 0.72% uranium-235. We are talking about 0.6 million megajoule per kilogram. And if you use enriched uranium, that is 3.7 million megajoule per kilogram. So for us to reach, as we suggested on the Kardashian scale, even the level 1 of a technological civilization, we need to use all our resources on Earth, and that includes the wind, the solar, tidal energies, in addition to nuclear energies. This is the wave of the future because the fossil fuels are depletable. They are not going to be there in our future. Since we are talking here about tremendous amounts of energies, then we need to understand the terminology. The terminology is for large amounts of energy, we use the unit that we call the quad. The quad stands for is an abbreviation of quadrillion. And you know the scale, 10 to the 6th power is a million, 10 to the 9th power is a billion, 10 to the 12th power is a trillion. If you go another 3 orders of magnitude, 10 to the 15, that's a quadrillion. So it's abbreviated as 10 to the 15 in the British thermal of units. That's a British thermal unit. The quad is different than the Q. If you say Q, that is another 3 orders of magnitude higher, 10 to the 18th BTU, or British thermal units. In the SI system of units, we like to use a trillion gigajoule, so that's 10 to the 12 gigajoule. It is approximately equal to 1 Q here, the 10 to the 18th BTU, but it's 0.948 Q. So you can say that 1 Q is 1.05 trillion gigajoule in general. The fascinating thing, if you go back to the Sankey diagrams that we dealt with earlier, is that in the United States, the utility industry typically produces 33 quads of uses 33 quads of primary energy, nuclear, coal, natural gas, wind, solar, and so on. 18.4 quads of that 32 quads is in coal. So almost 1/2 of the primary energy that we use still in the United States is in the form of coal. The net result is that we produce 11 quads of electricity. So if you take that electricity as being the product of the energy production process, at least in the United States, that we are rejecting to the environment 22 quads to keep the flow system in all the systems of energy production. However, you'll find that that electricity, 10.7 quads, divided into the primary energy, 32.8, tells us that we have an efficiency overall in the energy supply system of only 33%, which means that we are using 1/3 of the energy, the primary energy that we are using. So there is lots of room to improve on that efficiency by using more efficient systems in general. There is a tendency, as I suggested, to use first high energy density or specific energy sources of energy, but there is also a tendency to use more hydrogen in the sources of energy that we use. We start with wood in England at the beginning of the Industrial Revolution. The hydrogen to carbon ratio, how many hydrogen atoms to carbon atoms we have, is only 0.1. When England switched to coal after they used up all their wood resources, they had to go mine coal. They found that coal floating on the waters, some black kind of stones floating on the water of the North Sea. They went after wood, and you could see that increased the amount of hydrogen to carbon ratio by a factor almost of 10. Then oil came, and you notice that oil doubled the amount of hydrogen to carbon. We have many, many different types of petroleum or crude oil, different compositions in different parts of the world. It ranges from 0.8 to 1.5 to 2 in light sweet crude that comes, say, from Saudi Arabia. Heavy sour crude comes from places like Venezuela and the tar sands of Canada. And we have many different types of alcohols like methane, gases, methane, propane, hexane, cetane, and all of these have in the range of 2 hydrogen atoms per carbon atom. When you go to methanol, methanol is an alcohol now that is based on methane. So if you combine that CH4 here with some oxygen from water, you get an alcohol, methanol, obviously, CH4, the methane. In that case, the carbon to hydrogen ratio is 4. If you use another alcohol, ethanol, that ethanol is an alcohol too. It has a different composition, less hydrogen to carbon ratio, but it is more like plant-based from the fermentation process. In the United States, we use the fermentation of the starch of corn. In Brazil, they use the fermentation of the sugar from sugar cane. If we switch to a fully hydrogen economy, well, the hydrogen to carbon ratio, carbon is 0, so hydrogen becomes an infinity. The hydrogen to carbon ratio becomes infinity. So that is a goal of our future supply systems of energy. All right, if we use hydrogen as, in that case, it replaces a battery. It stores the different forms of energy, whether it's nuclear, wind, solar, and so on. And then you use it in what we call the fuel cell. So how does the fuel cell works? The fuel cell simply uses after dissociating the water in the reverse reaction. So think about that reverse reaction here. H2O, if you add electricity and heat, you dissociate it into hydrogen and oxygen. In the fuel cell, it's an electrochemical process, half chemical, half electrical. You'll find that in the fuel cell, the hydrogen molecule splits into 4 electrons and 4 ions of hydrogen, and those electrons become mobile. And as they become mobile, we call this the oxidation half reaction. And a second reaction in the process takes those 4 free electrons, recombines them with those 4 ions of hydrogen plus oxygen from the air, and turn them back into water. So if you add up those 2 equations, the free electrons now cancel out, the 4 ions of hydrogen cancel out, and you are turning your hydrogen, you're burning your hydrogen or oxidizing your hydrogen back into water. So hydrogen in that case is like a battery. People like to call it an energy carrier. It is not a fuel by itself. It's a way of storing other forms of energy in the forms of hydrogen in that case. The first ever fuel cell was built by a gentleman in France called de Grove. And here he shows us his fuel cell. You notice he's the oxygen, the hydrogen in inverted tubes in water. And he suggests that when you circulate a DC, direct current in the water dissociates into hydrogen and oxygen. He has a mistake in his diagram here because you'll have 2 molecules of hydrogen for 2 atoms of hydrogen for 1 atom of oxygen. And then he thinks about a perpetual kind of a machine is that oxygen and hydrogen, if you recombine them back again, that provides the current to dissociate the water. A modern fuel cell obviously does not depend on a perpetual type of a machine. It depends on electrochemistry. So a composition of a modern fuel cell is shown right here. In that case, you use an electrolyte. The electrolyte can be a liquid or can be a solid, like acetate sheets that are used by some people for transparencies actually have been used in that case. The electrolyte would be placed in between an anode with a negative charge and a cathode with a positive charge. If you bring in the oxygen from the air on one side of that electrolyte here, and you bring in the hydrogen on the other side of it, a chemical reaction, the half oxidation reaction that I've shown earlier. Basically, you'll find that the electrons are freed out of the water, from the water. Now the hydrogen flowing on one side of the anode and the oxygen on the side of the anode recombine the hydrogen and the oxygen, and the electrons become free, and those free electrons can be sent into an electric motor, and that is the way that a fuel cell operates. We'll see in a small calculation right now that the voltage that a single unit of a fuel cell can generate something in the range, say, of 1.2 volts. Well, car batteries, if you want to use fuel cells in a car, we need a minimum of maybe 12 volts. So what do? You stack those small units. So in that case, you get a fuel cell stack. Each one of them produces a small voltage. If you place them in series, you get really the voltage that you want. And we'll consider a design calculation today. There are many different types of fuel cells. I'll just review them very quickly. The phosphoric acid fuel cells, this electrolyte obviously is a liquid in that case, but those two half reactions at the anode and the cathode, where the electrons become free in the external circuit, and now in that case can run an electric motor. It's the same types of reactions in general. Polymer electrolyte membranes have been used using Teflon-like backbones consisting of hundreds of repeating chemical units. Solid oxide fuel cells have been developed. There is lots of research going on along those fuel cells, all of them based on those two half reactions where the electrons become free in an external circuit. In the same way that the electrolysis process is encouraged by using heat, you'll find that heat is generated and we need to cool those fuel cells. Chemical batteries also, lithium-ion batteries, in fact, in electrical vehicles also need to be cooled. If you look very carefully at the Tesla car, you'll find an opening in the front there that brings in air to cool the batteries as they're producing their energy. The configuration becomes very simple in that you'd have an electrolyte, solid or a liquid. Then you get an oxidant, which has to be, it doesn't have to be separate from the fuel. In that case, the fuel containing the hydrogen. In that case, you don't need to use hydrogen per se. You can use a fuel that contains hydrogen, like methanol, like alcohol, for instance. You'll find that you have one layer of the cathode and an anode, in between them the electrolyte, and then you circulate the fuel on the top and the bottom through openings, and the process generates a voltage drop between one side, between the anode and the cathode in that case. And in the end, this is an actual fuel cell there, a stack of 3, 1, 2, 3. These are the openings where you circulate the hydrogen and combine it with the oxygen in general. There are direct methanol fuel cells. In that case, methanol is used. Methanol, as we suggested, CH3OH, contains 4 atoms of hydrogen. You'll find that just using alcohol can be a source of generating an electrical current in a fuel cell. This is very convenient for applications where you want, say, to power electrical equipment like a computer, not just for 5 or 6 hours, but maybe for 24 hours. Another type of fuel cells is the molten carbonate fuel cells, and it's left to your imagination how to generate those two half reactions, alkaline fuel cells and regenerative fuel cells. All right, now how do those fuel cells operate? Obviously, it is an electrochemical process. So the electrical engineers are involved in it, and as well as the chemical engineers and the mechanical engineers, all of us are interested in it. Now, the power that you deliver in a fuel cell is obviously, like in any electrical engineering process, the product of the current I multiplied into the voltage V. If I is in Coulomb, in amperes, and V is in volts, the power is has the units of watts. Now that voltage here is a differential in voltage in a fuel cell. And the electrochemistry part tells us that the delta E is equal to a minus here. Delta G is the free energy and the Gibbs free energy divided into the Faraday's constant, which we know is a constant in electrochemistry, 96.487 Coulomb or joules per volt. And N is the number of moles of electrons per mole of H2 in the reaction. For water, it's 2. So we have to remember that this is 2. That Gibbs function or Gibbs free energy change is described by the change in enthalpy, delta H minus T delta S, where delta S is the change in entropy. And that's why we call it a thermochemical process or electrochemical process, because the T here would be the Kelvin temperature. Remember, 273 plus room temperature. So if you substitute that delta G with a change in enthalpy minus T delta S, if you take into account the negative sign, it becomes T delta S minus delta H as the energy or the voltage drop that you can get from a single fuel cell. Let's use an example. I'll let you do the calculation yourself. Notice that it depends here, the voltage depends on the temperature. So T here is the temperature. So as a fuel cell generates temperature, we have to design the fuel cell for the temperature at which it will be operating. So obviously you can start operating a fuel cell at room temperature, but then the temperature is increased. You'll find that the voltage decreases in that case. So we really need to get a certain level of a voltage, say for an electrical vehicles, we have to take the operational temperature into account. So let us take two examples here. If you operate a fuel cell and you don't have heat generated at room temperature, you take room temperature as 25 degrees Celsius plus 273. This is the number of kelvins, 298. And at STP, standard temperature and pressure, you'll find that your delta E here, the voltage generated is T delta S minus delta H, T 298 kelvins. The change in entropy is for a typical cell minus 163 joules per Kelvin. The change in entropy in enthalpy, this is enthalpy H, S is entropy, minus 285 joules. You plug in the number and you find that you get a positive 1.229 volts. So in that case, we took delta S and delta H as typical value. Now, suppose that you operate that fuel cell at 100 degrees, 80 degrees Celsius. Let's take 80 degrees. That gives you a T here in Kelvin of 353. If you plug in the numbers, you'll find that you get a lower voltage. Instead of 1.229, you get 1.183. So in that case, you'll find that operating the fuel cell needs cooling. If you don't cool it, you get a lower voltage. Obviously, also when you say that I need to generate, say, 12 volts, 10 cells here are not going to be enough. You have to design it at the level of the voltage at which you are operating it. So you need maybe 11 cells. You cannot have 10.5 cells, obviously. You can use 11 cells in the design in general. So a voltage decrease is observed for higher operational temperatures. Hence, fuel cells have to be cooled in the same way that we have to cool lithium-ion batteries in Tesla cars. And as I suggested, the fuel cell is the main competitor, especially for long distance travel and for very high power needs for trucks. And I think Toyota is going to be the leader in terms of providing hydrogen as the energy source for driving trucks for long distance in general. The generation of hydrogen is not just feasible by using the electrolysis process or thermochemical processes. Some people have been doing research using microbial fuel cells. So in that case, basically use microbial action. You provide solar, actually using solar radiation to dissociate the water into the hydrogen. And in that case, CO2 is emitted from using sugar. But CO2 is emitted in that case, so we have to be careful about calling it 100% carbon free. Hydrogen, of course, is a challenge for engineers because hydrogen is extremely reactive in air. And we can remember seeing in our lifetime the hydrogen explosions that happened at the Fukushima accident after the reactors were flooded by the tsunami. But we know that hydrogen is very reactive from prior experience. It's a small molecule, so it also leaks from any metal containers. And you have to keep it at high pressure so those containers can explode. Hydrogen embrittles metals. In that case, you have to be careful how you store it. And a reminder for us as engineers of the challenge of using hydrogen is the Hindenburg dirigible, Zeppelin dirigible, coming here from a trip through the Atlantic from Germany to New York. And as it was landing at Elmhurst, New York, you could see here some of the ropes, maybe some situation happened, spark ignited hydrogen that was used for the buoyancy of the Hindenburg and caused the end of a whole technology. They were not used anymore after that. The Germans had to use hydrogen because the United States had a monopoly on the use of helium. And dirigibles were used in the First World War for directing artillery fire and for basically gaining intelligence on the troops from one side on the other. So the United States did not supply the Germans with helium. And that was a tragedy where many people died. Actually, it was filmed, so you can watch the film on YouTube of that whole dirigible falling down. A member of my family from parents-in-law basically died in that accident. So it is remembered on a national basis in general. Applications of fuel cells. Fuel cells started being applied in space. So that's a spin-off of the space program. NASA used it in the 1950s to generate electricity in spaceships, in manned space missions, because when you use it, you are combining hydrogen and oxygen. Oh, you get water. So your water can be used also by the astronauts. Fuel cells now are being used, in fact, in specialty vehicles, especially in cities where you get smog. To control the smog, you use the fuel cells. This is a 50 kilowatt fuel cell engine used for buses, maybe in Los Angeles, San Francisco, Chicago. In that case, you do the processing of material like methanol, alcohol, into a fuel reprocessing plant, into a reformer, and then you use the hydrogen in a fuel cell. A little carbon is released if you use methanol, obviously, but not as much as if you are using gasoline. Residential power, some applications are used already in residential power production. Defense applications in particular are notorious because in that case, when you use methanol as your source of hydrogen, your battery on a computer used in the field by the military can last for 24 hours. It is finding more applications also in handheld devices, but the main future for fuel cells really is in electrical vehicles. In that case, it is a competition to the use of the lithium-ion batteries. And in that case, you would have a hydrogen tank, as I've shown you earlier in the lecture. Here is a hydrogen tank in the back of your car. The fuel cell protect the fuel, the hydrogen tank, but from a collision from the back of the vehicle. And your electric motor now gets the electricity from the fuel cell to the front. You don't need to have the battery stack, a lithium-ion battery stack below the passengers or the driver, and you try to protect it in the back of the vehicle. Ford, basically the Ford company, all the car companies are interested in that type of an application, and it's going to become of our future. I discuss here the environmental necessity for getting a non-carbon economy for hydrogenation and decarbonization. I described to you here the very nasty warning that we get from the burning of coal. When they were burning coal in Belgium, 1930, coal was powering factories, led to 60 deaths and 6,000 illnesses. It happened in Pennsylvania. The emissions from coal are very unhealthy. And it is not known, but in the United States, we get 50,000 deaths per year due to air pollution. And 10% of 20% of them are attributable to coal burning. So let's take the lower figure, the 10,000, divided by the 2 million deaths that we have in the United States. So 0.5% or one of every 200 American deaths in the United States are people who are dying prematurely from the pollution from coal. The situation is worse in China in particular, because of the composition of coal in China contains lots of arsenic. It contains 35,000 parts per million of arsenic, and villagers in China mine their own coal from the hills and then burn it inside their homes to dry their crops. And compared with United States coal, it's only 22 parts per million of arsenic. So you could see there that in China, coal is causing to unnecessary health effects and death in general. So that suggests that, in fact, China is much more interested in producing nuclear energy to avoid the pollution and the deaths of its population and the bad health effects from coal. Since the cleaning up of coal burning technologies remains in large measure an exercise of wishful thinking, adopting hydrogenation effort using wind, nuclear, and solar sources becomes the logical way to proceed for our technological civilization in general. We suggest we're having a course on nuclear energy, so nuclear reactors definitely would be very useful in producing that hydrogen. And the energy that you produce from a graphite reactor that can produce high temperatures can be, in that case, use the high temperature gas-cooled reactor to produce the hydrogen. Another type of a reactor that we'll describe later on is the molten salt advanced, also high temperature reactor. Why is that? Because you can produce hydrogen from water with a combination of electricity and heat. So in that case, you use the high temperature electrolysis. This is used right now in Germany to produce hydrogen. But if we want to have a hydrogen economy, we need to develop high temperature gas-cooled reactors. The hydrogen produced from water, now in that case, the delta H that we use in the previous equation, the change in enthalpy, this is the energy that is required in the electrolysis process to decompose water into hydrogen and oxygen. And this is equal to the amount of required energy as in electrical form, delta F plus T delta S that's the energy required as heat. So T here is the temperature. If you put this equation on a diagram, you'll find something very interesting here, is that to dissociate hydrogen, if you use primarily an electrical input, you use a very large amount of electricity. Now remember, electricity is an expensive form of energy. That is heat primarily that has been turned into electrical power. And in that case, to maintain the flow from the high temperature reservoir to the low temperature reservoir, we have to reject some energy to the environment. It turns out, according to that dissociation equation for water, that if you add heat input, so if you add heat here, the combination of the electrical input and the heat input still adds up to that delta H, and you still can dissociate the water. In fact, at some point, you reduce the amount of electricity to 0, and you can dissociate water just by adding a very high temperature. So if you want to produce hydrogen from water efficiently, we need some heat input, and that process is called the high temperature electrolysis. Now, let us discuss the process. If you want to produce hydrogen, you have to do two things. You have to produce electricity and you have to produce heat. Now, the electrolysis process has a very high efficiency, 0.9. So the efficiency of the hydrogen production is now the product of the efficiency of the electrical production process multiplied into the efficiency of the electrolysis process. So that's 0.4, say, for a typical high temperature gas-cooled reactor, multiplied into 0.9 at a 36% efficiency. Now that electrical efficiency here, 0.40%, as we suggested, is typical of high temperature gas-cooled reactors. If you continue using light water reactors, that's only 30%. 30% by 0.9 becomes a very low efficiency that makes the process uneconomical. So if you want to produce hydrogen for a future transportation system, we have to think very seriously about switching our nuclear power plant to the high temperature ones in general. So in the high temperature electrolysis, you find that a large fraction of the range of 30 to 50% is supplied as high temperature heat. Why high temperature heat? There is another reason, because there are also thermochemical hydrogen production processes. The iodine sulfur process uses high temperature. And let's look at the equations for this. You start with sulfuric acid, you heat it up. As you heat it up, you release sulfur dioxide, oxygen, and water. You add iodine to that sulfur dioxide, and notice what happens here. An exchange process happens where the hydrogen combines with the iodine, and then the hydrogen iodide simply dissociates into iodine, and hydrogen is released. If you add the equations, you'll find that you can recombine it back again. The water plus the hydrogen plus the oxygen gives us back the iodine. So this is a high temperature process to produce the hydrogen. The electrolysis process in that case could be 80% efficiency, and you get a meaningful efficiency by operating at high temperatures in the range of a 40% efficiency. Some people suggest that the process is of producing hydrogen is inefficient. True, in the case if you use low temperature processes like the light water reactor, but if you want to use nuclear energy, you have to go to high temperature gas cooled reactor, and I hope I made a justification for the process. So in general, our energy supply is being hydrogenized, decarbonized. That should be the incentive to constructing a new generation of nuclear fission plants, eventually maybe the development of safer fusion system. This would be in addition to whatever other supplies can be provided with wind and solar energy methods. We are decarbonizing our energy system today. Hydrogenation is the wave of the future. And I thank you for your attention. And in that case, I'll stop at that point and see if you have any question in the chat room. We have another hour to go for some other material. So if there are no questions, I'll start on some other type of a system that we'd like to deal with. I need to, am I sharing right now? Anshal, maybe, yeah, I am sharing. Another type of a reactor is the, that have been very successful, and it was developed by the Canadians in general, is the heavy water reactor. The heavy water reactor, as I suggested in an earlier chapter, uses heavy water as a moderator and a coolant. Now, heavy water contains deuterium rather than hydrogen as the component of the water itself. And deuterium is not a very strong absorber for neutrons. So in that case, if you use heavy water, you can use natural uranium, and you don't have to go through the 3 to 5% enrichment that we need of uranium in light water reactors. For a country that doesn't need to depend on a supplier of its enriched uranium, the option in that case becomes very, very favorable. So you find that the Canadians didn't want to be dependent on their energy supply from nuclear energies on the Europeans, the Russians, the Japanese, who have the ability of enriching uranium-235. So they developed the heavy water reactor, especially that they have lots of electricity available to us in the area of the Niagara Falls, and so they use electricity to produce heavy water. The Canadians are very proud of their development of the heavy water reactor. They call it the CANDU system, Canadian Deuterium Uranium. That's the acronym for it. You could see here that is their first generation plant using heavy water reactors and natural uranium reactors. It has been decommissioned. It's just aged, and they are building newer, more modern system, but they commemorated that first generation with a stamp. And they could see in Canada, everything should be both in English and in French. So peaceful uses of nuclear energy. And they show that particular plant, Douglas Point, and in French, utilisation pacifique, peaceful uses of nuclear energy. Many countries in the world, in fact, have that type of a design. Again, they don't want to depend on, they want to depend actually on their own supplies of natural uranium as a fuel, and not have to be dependent on other countries supplying them with enriched fuel. The CANDU design is a very successful design. It is built with large units. So you could see here we have 1, 2, 3, 4 units of the CANDU with an older unit shown here. But in the background on Lake Ontario here, you'll find those towers here. These are the towers that produce the heavy water for those reactors. So instead of enriching the uranium to the 3 to 5%, they have to enrich their heavy water, the water into the heavy water for these types of reactors. And the latest type of designs, that's the second generation, that's Point Le Pro. This is now the design that they designate as CANDU 6 power plant. The Canadians are very proud, and it's a very nice system. In fact, it can operate at a very high capacity factor. So let's look at the design of those heavy water plants. Now, because I use natural uranium, as you know, natural uranium is only 0.72% uranium-235. So you end up burning that uranium-235 quite rapidly. And because you burn it rapidly, you need to continuously feed fuel into your reactor. So they had to adopt an online refueling system where they have now, instead of the vertical tubes in the PWR and the BWR that is enriched fuel that has to be only refueled once every year, here they have tubes, and from the face of those tubes, they feed bundles that contain the uranium, natural uranium fuel. And those tubes also have connections that bring in heavy water as a coolant and as a moderator. Very much like the very early designs adopted in the United States for the production of production reactors at Hanford system. So what they do is that they feed a bundle from one side, it pushes the bundles in a vertical tube, and from the other side, they have another machine that extracts the bundle of energy. Look at that gentleman here, that gives you an idea about the size of a typical heavy water horizontal reactor. So the typical of it then of the CANDU reactor is its horizontal design. It is a nightmare of tubes, as you could see here, a plumber nightmare. Those tubes are immersed in a very large tank, contains heavy water. As a safety feature, if there is an accidental occurrence, that heavy water can be dumped out of that tank. And if you dump the moderator out away from the fuel, the chain reaction cannot proceed and stop itself right away. So these are all tubes where the fuel is fed from the front, extracted from the back on an online basis. And because it is on an online basis, you'll find that the capacity factor of that type of a plant is quite large. You don't need to shut it down as often as a light water reactor to replace all the fuel, because you are really feeding it online. A bundle of that fuel is shown here. It's maybe 2 feet in length, with the uranium dioxide used, the same as light water reactors, except that it is natural uranium now. It is not enriched uranium. There are spacers that space them from each other, and the coolant passes along the surface. In fact, it uses the same cladding as light water reactor zirconium alloys in general, but that bundle now is fed from one side of the reactor, and you bring in another one that pushes that bundle to the other side. So they end up with a feeding machine and on one side, they call it the charge machine, and an accept machine on the other type of the reactor. Now, the feeding machine uses a fuel that you can carry in your hand. It's not very highly radioactive in any way, but once the fission products have been formed, you'll find that the radioactivity becomes very large. So that feeding machine has to cool the fuel, take it as a spent fuel port, and immediately cool it under water, store it for a period of time until that it is decided whether to reprocess it or not. This is a dismantled turbine, just to show you the component of those wonderful steam turbines. This would be the electrical generator on the same axis as the turbine, and you could see here the steam comes from this side. The top of the casing has been removed for maintenance, as you could see here. The steam comes from the top, expands in this direction, expands in this direction. The two forces cancel each other, otherwise it will move like a rocket in general. The CANDU reactor has a very high performance. We describe the performance by what we call the life capacity factor. It is the total generation, TGG, the gross generation in megawatt electrical hours, divided into the capacity factor. Capacity factor is a time fraction over which the reactor is producing electricity. divided into the number of hours of operation. So the CANDO 6 designs have a very high LCF, or lifetime capacity factor. So let us compare the operation of the CANDO reactor to other sources of energy. This can be described by what's called the levelized unit energy cost. Levelized means that it takes into account the inflation and the interest rate over the lifetime of the unit that produces electricity, being a wind turbine or a nuclear reactors. The units are cents per kilowatt hour. How many cents basically you pay for 1 kilowatt hour of energy produced from different sources of energy. Notice here that the x-axis is the average capacity factor. And we suggested that the CANDO has a very high capacity factor because it has online refueling. So if you compare it at a high capacity factor to coal or natural gas, the CANDO reactor comes in really a winner at maybe 2, maybe 3 here cents per kilowatt hour of electricity, $1989 in that case, less than coal and less than natural gas. If you would have operated it at a low capacity factor, say 10%, notice that the price of electricity would be 12 cents per kilowatt hour. And in that case, natural gas maybe at 20 here would be the leader, followed by coal, followed by the CANDO. So the fact that the CANDO reactor is being operated at a very high capacity factor makes it more profitable, and in terms of the price of electricity, than natural gas, and even less than coal. So far, the problem is what do we do with the spent fuel? The spent fuel contains a large amount of radioactivity upon discharge from the reactor core, and the beneficial way to do it, like in the different fuel cycles that we looked at in some previous chapter, you recycle it and extract the unburned uranium and the unburned fissile fuel like plutonium, and burn it back as a mixed oxide of plutonium and of uranium. Until that decision is reached, you'd like the fuel, before you send it to a chemical plant, to have as much as possible of its radioactivity decrease. So the Canadians simply get their spent fuel and store it in those silos here by the sites of the nuclear power plants, awaiting a decision after the fuel, the radioactivity of the fuel decreases to a manageable and more economical effect for recycling in general. And so the system is very efficient, but it cannot be licensed in the United States for a very simple reason. The deuterium in the heavy water interacts with the neutrons and produces tritium. Tritium is an isotope of hydrogen that, as we know, is radioactive. In fact, the Canadians separate the tritium and sell it to the United States and China, maybe even Japan, for applications in all our LCD displays, like the phosphors on our liquid crystal displays on your computer right now or on your phone contains a very tiny amount of the tritium. The tritium is a beta emitter. It is not emitting gamma radiation, so it has a fascinating use in our modern technology. But tritium is radioactive, and hydrogen, it is hydrogen, in fact, chemically. It can diffuse through any kind of metals. So in the United States, the regulatory agency set up a condition that that tritium can leak from the CANDO reactors, and that would not license it in the United States. Great loss to the United States, obviously, because it's a very efficient and very desirable system to have in the fleet of nuclear power plant. That, however, in other parts of the world, because of its the advantage of using natural uranium rather than using enriched uranium, and depending on a fuel supplier that can deny the source of fuel to a country if it doesn't abide by its political whims. So many countries in the world use that heavy water reactor. You find countries like Pakistan, South Korea, some South American companies using in general. The heavy water reactor, in fact, remains a world leader in terms of reliability, a very high capacity factor, and power production. There were 39 heavy water reactors worldwide and 8 under construction. That was an earlier time, so I think it's the same by today. The number of countries operating heavy water reactors are 7, with a total generating capacity of 20 gigawatt and a substantial history of very safe operating experience. And that is our heavy water reactor. If we talk about heavy water reactors, we have to now talk about the fast breeder reactors. Fast here means doesn't suggest that the reactor is running fast. It's that we are dependent on fast neutrons. And the advantage of using fast neutrons is that when they cause fission, they can produce extra neutrons that can be used and absorbed in the uranium-238, which is part of the fuel, to produce fissile fuel, plutonium-239 in the case of the uranium-238 plutonium cycle. The fascinating thing that is really unique in nature is that the fissile fuel that you produce can exceed the amount of fuel that you burned at uranium-235, up maybe to a range of 20%. So this is the only process in nature where, as you are producing energy, as you are burning the uranium for producing energy, you'll find that you are producing more energy than what you consume. And this is unique to the fast reactor systems. It is really the vision of the future of nuclear energy. Today, we have supplies of uranium-235 that are very cheap, like $30 maybe per pound. So in that case, fast reactors have not been widely adopted. But an unknown fact is that the first reactors ever built, in fact, were fast reactors. And see here, this is a picture of the experimental breeder reactor #1 in the Idaho desert. If you travel through Idaho, it's a desert until you reach the west coast. And it was built up in the desert by the Idaho National Engineering Laboratory. One of our wonderful TAs is having some kind of stay there for the summer. Don't make sure you visit the site of the EBR-1 for Einschall. And here it is in the desert. It has been turned into a museum, and it used a liquid metal eutectic. Eutectic is an alloy that has a lower temperature than the component of the alloy. So if you combine sodium and potassium, basically it is liquid at room temperature. So that is a precursor to what is suggested today as sodium or lead bismuth as coolants for those fast reactors. Why lead? Why sodium? Because they're not good moderators, like hydrogen in water or deuterium in heavy water, or even carbon in graphite. In that case, they do not moderate the neutrons, but a liquid metal have a high heat capacity, so it can extract a large amount of energy. So in that case, the uranium-238 becomes a fertile isotope that can be turned into fissile plutonium-239. So EBR-1 was a fast reactor, the first reactor ever. And you could see here, they show us strings of light bulbs that use the first ever electricity produced from EBR-1 in December 20, 1951. That was the first production of electricity on American soil. It was followed by a larger reactor in the area of Idaho Falls. Maybe Anshal can visit it too. It was designated as the EBR-2. And it was a very well-designed fast reactor. I had the pleasure visiting Idaho Falls to walk on the top of the reactor while it was in operation. It tells you that it was very well shielded. It operated for around 20 years, providing electricity to the city of Idaho Falls. This one did not use a potassium-sodium eutectic. It used a sodium coolant only. Remember that sodium at room temperature is solid, so it has to be kept at some amount of heating. It operated for 25 years successfully. It used a pool concept that was adopted later on, but I'll show you by the French for their own breeder reactor. This team comes here from cooling towers. Also, it is built close to the city of Idaho Falls in Idaho. Now, the interesting thing about the EBR-2 is that it is a pool concept. You find the core here inside a large pool of sodium. You have pumps circulating the sodium. An advantage of using the sodium there is that it is not operated at high pressure. It's operated at atmospheric pressure. So in the case of a loss of the cooling of the system, that sodium cannot be lost by evaporation like in existing light water reactors that are pressurized 2000 psi in the pressurized water reactor and 1000 psi in the boiling water reactors. Any break in the piping in the PWR or the BWR would make now that very highly pressurized water see the atmospheric pressure, it flashes into steam and you lose your coolant. Not so with a sodium cooled reactor because it's operated at atmospheric pressure. Well, still we have to be careful here because sodium is highly reactive with air, with oxygen in the air, so it must have an inert material like neon gas on the top to prevent the sodium from interacting with air. That reactor has been experimentally shut down and the decay heat simply released to the environment by a very simple heat exchange. Now, another situation there that we have to worry about is that, as we suggested, sodium in the core of the reactor circulating and cooling the core absorbs a neutron and becomes sodium-24, which is a very strong gamma emitter. So in that case, the sodium is cooling the reactor. We cannot send the sodium directly to a water, sodium to water heat exchanger. In the case of leakage between the tubings and the water, sodium is highly reactive. In fact, lithium-ion batteries also are very reactive. Sodium and lithium are in the same column in the periodic table of the elements as metals. So in that case, you have an intermediate sodium loop. So you have a sodium loop cooling the core here. It sends the energy to another sodium loop that does not see neutrons now, so it doesn't become radioactive. And then that second loop of sodium goes and generates a steam that goes to the turbine to produce the power. So this is the flow diagram of the EBR-2. The United States had a project to build a fast reactor, and they called it the Clinch River Reactor. They gave the design to the engineers at the Westinghouse company, and they came up with a design to be built in Tennessee, being cooled by the Clinch River. But they were too lazy in their design. Instead of adopting the pool kind of a concept, they redesigned it in the shape of the similar pressurized water reactor with lots of tubings that can be affected by and broken by an earthquake. Upon review by the engineering community, they told the Westinghouse company, no, why didn't you use that type of a design? That is a more efficient design for a system that would use a liquid metal. And the project was simply forgotten, and there haven't been fast reactors built in the United States since then. This is more the detail about the design. You could see here the core of the reactor is in a pool. The Clinch River design that Westinghouse came up with was a loop design, like the pressurized water reactor. And basically the Clinch River design was forgotten. This shows us pumps, impeller pumps used to circulate the liquid metal. A better option would have been to circulate the liquid metal with magnetohydrodynamic pumps that would not have an impeller and simply would move the water through the Lorentz force in general. So this is the core inside the pool of water rather than the loop design, read pool in the opposite way, loop pool of the PWR and design. This is a design of the core. The core has surrounded, this is the core here, but it is surrounded by a blanket, as it's called, that contains uranium-238. This is the core here, intercepting neutrons and producing plutonium-239 that would be recycled and used as a fuel. And as I suggested, you can produce more fuel than what you have consumed to produce the same amount of energy. In the 1940s, fast reactors were considered as really the way to go. So the Clinch River was designed in the United States, but many countries actually built fast reactors. In the UK, for instance. The ones that really adopted the process is the French. And the French redesigned it for a larger reactor, and they called it the Phenix Reactor. The French are very poetic. The word Phenix, of course, relates to a mythology bird, and mythological bird that supposedly is burned, but it gets reborn back again from its own ashes. So that's a very poetic description of the breeding process, is that as you are burning the fuel, you are creating more fuel from the ashes of the fuel that you have burned. They followed it by a larger reactor shown here. Now they called it the Super Phenix. And both of them operated, as you know, France produces 70% of its electricity because they're short on fossil fuels. It produced a breeding ratio of 1.2, but it didn't spread because, again, the cost of uranium, natural uranium, is very cheap. Light water reactors still predominate in the production of electricity. The fascinating thing is that even though the United States went with Westinghouse into that PWR-based design, the French did, in fact, do the right thing. And if you see here, the core inside a pool of the liquid sodium as a coolant in that case. So the French were smart enough to adopt the technology that was developed over 25 years here in the United States in the EBR2, or Experimental Breeder Reactor number 2. If you find your way to Idaho Falls, make sure that you visit the museum site of EBR1, Experimental Breeder number 1, as well as maybe the EBR2. I don't know whether it's open to the public. This shows us a coolant circuit for the Super Phenix. 2 sodium loops. One goes through the reactor, is activated by neutrons, radioactive, sodium to sodium, and then sodium to produce steam in the turbines right here. For the future, obviously, the use of the pool design for fast reactors with the sodium, the one safety feature, obviously, is that it operates at atmospheric pressure. Because it operates at atmospheric pressure, it cannot flash into steam like in light water reactors. However, technologically, it's more difficult to design because you have to avoid any contact through cracks from manufacturing between the sodium coolant and the water coolant, because sodium, like lithium, is reactive with water. This shows us the different regions of the reactor core. One region would contain uranium-238, intercepting neutrons so that you can breathe the fissile fuel plutonium into it. It had an elaborate fuel handling system. You could see here that the fuel is taken out of the core, cooled continuously and stored from the reactor here and stored in fuel storage pools that are where the fuel is stored underwater pending a recycling of the fuel itself. These are some details of the fuel assembly, and it was built, it operated successfully. It generated a breathing ratio of about 1.2, meaning that it did produce, in fact, the vision of nuclear energy for the long term, where 20% more fuel was produced compared to the fuel that was burned in general. The Russians developed their own fast reactors too, the BN500 and the BN800. Let me see if I have a picture of it. This is one fast reactor that they were constructing at Beloyarsk, the BN800. 800 stands for 800 megawatt electric. The UK and Japan have projects also on fast reactors. They would be using what's called the mixed oxide fuel. And in that case, it's a fuel that is a mixture of uranium dioxide and plutonium dioxide. It seems that its time hasn't come yet, but it will be part of our future as achieving the vision of nuclear energy, where you have, if you produce more fuel than what you are burning, you have an unlimited energy supply. That is so obvious. All right, so this was the both the heavy water reactor and the fast breeder reactor. At this point, I would like to use the rest of the lecture to talk about what is being considered as the future type of nuclear power plants, the ones on the drawing board. And that is described by what we call the fourth generation reactor concepts. The fourth generation reactor concepts have a vision into maybe using hydrogen. As I suggested in the first chapter today, that could be used as a transportation fuel and with fuel cells, with water as a non-polluting, even though it's a greenhouse gas water, but the water that you dissociate into hydrogen and oxygen, you remake back again. That's a net water into the atmosphere. You remake it again when you burn your hydrogen or in the fuel cell. So in that case, you find that some of the generation 4 reactors would be considering the the production of hydrogen for a future transportation system. So let's look at 6 designs that are on the drawing board. Some of you may take part in developing, constructing, and operating those nuclear power plants. Right now, we are at the 3rd generation on land-based reactors, even though naval reactors are at the 9th generation. So in that case, the land-based reactors can take some inspiration from the developments of the 9 generations of naval reactors. Naval reactors are really very compact in size, and lots of technology has been developed beyond what we have in land-based systems. Some technology was adopted, like the canned rotor pumps that are used in boiling water reactors today. A 3rd generation plant that is under construction is the AP1000 and AP600, both licensed in the United States. You could see the containment structure here, having the chimney on the top. There's those openings that provide cooling for the steel containment structure. The steel containment structure has been introduced into the advanced passive 1000 megawatt electric, in that case, the design. Many of those systems are being built right now around the world, and are built by an alliance between Toshiba, Japan, and Westinghouse, United States. In fact, Toshiba owns Westinghouse right now, but the Westinghouse plants and company are based in the United States. So we are talking about several generations of land-based reactors. The first generation was built from 1950 to 1970. Some of the reactors are like Dresden here in the United States, and the Magnox. Magnox stands for magnesium oxide reactors in the UK. These were followed by a second generation of nuclear power plants. This would be the light water reactor that we have today, the pressurized water reactor and the boiling water reactor. And that also includes the CANDU, the Canadian uranium, as well as in the Soviet Union, and followed by Russia, the VVR 1000 and the RBMK 1000 that was involved in the Chernobyl accident. Third generation, as I suggest, includes now the advanced light water reactors, or designated as ALWR, and the advanced boiling water reactors. In the United States, AP600 and AP1000, as I described in the chapter on the PWR, are licensed to be built in the United States. The fourth generation that we are talking about now in this chapter are the ones that are on the drawing board for the future. They haven't been built yet. They are meant to be economically competitive with coal in particular, that they should have enhanced safety over the existing systems. And they also need to minimize the generation of radioactive waste, and they should be proliferation resistant. We don't want unstable governments in states to be lobbing nuclear weapons at each other. The initiative is called the Generation 4 Initiative. It has 10 countries taking part in it. These are the USA, the UK, France, Japan, Canada, Argentina, South Korea, South Africa, Switzerland, and Brazil. The criteria is basically to generate a new generation of nuclear power plants that are sustainable, and different fuel cycles are considered. The once-through fuel cycle that is now used in the United States. In the United States, the fuel burned in nuclear power plants is taken out and just stored at the site of the nuclear power plants, pending a decision on how to recycle them. There is another consideration, is a fuel cycle with partial recycling of that bred plutonium, and then you use that plutonium dioxide with uranium dioxide in what's called the mixed oxide to fuel existing or future power plants. A full plutonium recycle cycle is also under consideration, and that would achieve the vision of nuclear energy. You would be producing more fuel than what you consume. And another cycle that recycles the transuranic elements that are produced to minimize the amount of radioactive waste from existing power plants. And the transmutations is an interesting feature here, because without transmutation, the relative toxicity of a repository where you store the fission waste from nuclear reactors, you'll find that you reach the same level of radioactivity as natural uranium in the range of maybe 300,000 years. So if you really want to produce a fuel that has the same level of toxicity as natural uranium, you need to use transmutation. So in that case, let's say here, 500 years time, the relative toxicity in the repository would be at the same level as natural uranium. So it's the same way as you mine the natural uranium. It is radioactive from the ground, and you return the fission waste at the same level of toxicity reached after 500 years. So in that case, these are all options that are considered as features of the future generation of generation 4 reactors. Well, the first one that we have to consider definitely is the one that has to do with the first chapter, what we covered today. And in that case, you use very high temperatures. With very high temperatures, you can dissociate water through the high temperature electrolysis effect and approach, I would say, as well as the chemical processes like the sulfur, sulfuric acid, iodine process that I briefly described today. In that case, you have to operate at very high temperatures. So one of the 4th generation reactors is a very high temperature the reactor, and the people at the Idaho National Engineering Lab provided us with a diagram that describes that process. They show us a reactor here and producing steam, and the steam is taken here. Look at that whole plant here is just a hydrogen production plant. It is said that $1 million have been 1.1 billion has been budgeted for building a pilot plant along this line, except that the design here is not very perfect. If they want to get very high temperature, they cannot use a steam producing system here, a light water reactor. They should think, well, they're thinking about a graphite reactor core, but here they're using a steam cycle. Why use a graphite core with a steam cycle? That graphite core should use a gas as a coolant, and if you use a gas as a coolant, you need to use the Brayton cycle, not the just produce steam. Well, it's a principle, in principle, supposedly very high temperature steam that would have a generation of hydrogen. So the product is hydrogen for the use in fuel cells for a future transportation system. So that would be our use for the reactor in general. Another reactor that can produce high temperature and that also breeds fuel is a gas-cooled fast reactor. Now, it would be gas-cooled, but a fast reactor meaning that the moderator is not going to be graphite, sodium. Actually, it's a gas-cooled reactor, so you don't need a moderator at all. In that case, they show us a diagram also, the wonderful people at the Idaho National Engineering Laboratory. And here it is now. Notice here the difference between the two designs. Here, steam is produced in the reactor core. It goes to a turbine, expands in the turbine, goes to a recuperator. And look here, you have a compressor now on the same shaft as the turbine. So in that case, they are using a system to produce primarily electrical power, not heat like the very high temperature reactor, but the use of fast neutrons allows the breeding of the fuel. So you produce more fuel than what you consume, getting closer to the vision of nuclear energy as an unlimited energy supply. Again, when you see the turbine on the same shaft as the compressor, this means that they're using the gas turbine cycle, the Brayton cycle, rather than the steam cycle in general. I'm listing the reactor designs in the generation 4 reactors on the basis of their ability to produce high temperature for basically the dissociation of water into hydrogen oxygen that we started our lecture on today. A very promising process is to go back to what we called the liquid metal fast breeder reactor that we covered today. And you could see here that they have totally ignored the loop design by Westinghouse that was used for the Clinch River design that was simply abandoned because it was not technologically sound. Here you are using the pool concept, the same as used in the EBR2, the same as used by the French in their Phenix and Super Phenix, and by the Japanese and the British and the Russians in their BN800 and reactors. So in that case, you produce steam at high temperature in a pool of sodium and take it to a steam and just turbine. They're not worried about producing high temperature steam. What's missing in their diagram is that there should be a secondary sodium to sodium generation process. So if you use those diagram in an actual design, be aware of that. That is a sodium fast reactor. It's really a repetition of the idea of the liquid metal fast breeder reactor. Another fast breeder reactor now uses, instead of using sodium, uses in that case lead. Actually, not just lead, but in that case, it's an alloy of lead and bismuth. So it's either lead or bismuth-less eutectic liquid metal reactor. And in that case, you would have a very deep type of pressure vessel. You have a core at the bottom here. The coolant as lead bismuth extracts the heat from the reactor, rises, and then transfers the heat to a heat exchanger where they're using a natural, they're using a gas turbine. In that case, you could see here the gas is heated, goes to a turbine, expands to a recuperator, a pre-cooler, and to a compressor. So they're using a gas-cooled cycle or the Brayton cycle. One interesting aspect of that design is the use of the chimney effect. The chimney effect is used in our chimneys, obviously, where the air, the hot air from a chimney, when you burn logs of wood, say, in a home, the heat rises and goes out of the chimney. But the chimney effect here is in such a way that as the heat is transferred to the lead bismuth in the chimney here, it loses its heat to the heat exchangers and cools down. As it cools down, the density decreases and the lead and the bismuth go down and generate natural circulation. And that's a neat thing. In that case, you don't need pumps to pump the water, and that is a safety feature as well as, of course, you save on maintenance, and you save also on the capital cost. The use of lead and lead bismuth as a coolant was adopted by the Russians in one of their generations of nuclear killer submarines, the Alpha class of submarines. And one problem of using lead as a coolant is that at room temperature, it becomes solid. So they had to run the reactors on those nuclear submarines. They had to keep the lead molten at all time by using steam. And as you know, lead is very corrosive with metals. So they had to abandon their class of nuclear submarines and drop the cores in the Baltic Sea. Excuse me. Here the challenge, of course, is to develop materials that can take the very high corrosion from lead or lead bismuth. It would be a fast reactor because lead, like sodium, is not a good moderator for neutrons. And you use fast neutrons in that case to produce more neutrons for a breeding process. So in that case, you produce more fuel than what you consume. Another reactor that can produce very high temperatures had been developed by Germany and by South Africa. In that use, they use steam, but steam above the critical point in the TS diagram. So in that case, the water as steam is used, and you use supercritical water here. So it's really a different way of using the light water reactor to reach high temperatures, but still low and not high enough to use it for the production of hydrogen. And basically they use a steam cycle shown here, a turbine producing electricity from an electrical generator. Another, the last system that is really very promising is the so-called molten salt reactor. Now the molten salt reactor does not use a liquid metal. A liquid metal is different than a molten salt. The salt would be like sodium chloride, for instance. That's not a liquid metal. Sodium per se, alone would be a liquid metal. Sodium chloride is the salt, table salt. The molten salt reactor can be run with thermal neutrons or can be run with fast neutrons. And one aspect of the molten salt is that it would contain a mixture of thorium and uranium initially. The uranium fissions generates neutrons that would be absorbed in the thorium, turning it into uranium-233. Then you extract that uranium-233 and use it instead of the uranium-235. So that's a breeder system that breeds from thorium. And as it breeds from thorium, first it can produce high temperatures because it's a molten salt. So you can use here the Brayton cycle or the gas turbine cycle. You see a turbine with a compressor on the same shaft. You can produce high temperatures for the dissociation of water into hydrogen and oxygen. And it is can be used as a fast reactor or as a thermal reactor. This would be here a thermal reactor if it contains graphite as a moderator. And if you don't use the graphite as a moderator, they can operate it as a fast reactor. One advantage of the molten salt is that it's a liquid. A liquid is an evolution over our use of solid fuel in existing power plants in the light water reactor. Why is that? In the First World War, the British fleet used coal in the steam turbines that the British use in their fleet, basically to control the rest of the world. Came in the discovery of petroleum in the Gulf region. Winston Churchill in England ordered all the British fleet to convert from coal to petroleum. Using a liquid fuel is much more convenient, as you can tell, than a solid fuel where you have to shovel the coal into the boilers of the ships in the British fleet. The molten salt here is now a liquid. So you can circulate the liquid rather than leaving it in the core of the reactor. The Fukushima accident, the 3 Mile Island accident, and the Chernobyl accident all had the core melt down because of the decay heat of the solid in the core. In the case of the molten salt reactor, you associate it with a chemical plant that would continuously extract those fission products that would produce the decay heat. So you get rid of a problem that has been the cause of the 3 most major accidents that happened in the nuclear industry by eliminating the fission products as the reactor is in operation. Another interesting safety feature is that if the fuel, the temperature of the core increases, you have a plug here that is frozen. You'll find that the coolant would be dumped into dump tanks. And if the coolant is dumped out of the core, you don't have a chain reaction. So this whole system shuts itself down by itself without intervention by the operators. Pilot plants have been built, one particularly at Oak Ridge, Tennessee. They're showing it here using a Brayton cycle so they can produce high temperatures for a hydrogen producing system. And I am some kind of emphasizing that light water reactors should not be the option for us to build a new fleet of nuclear reactors if we want to think about a transportation system based on fuel cells and hydrogen fuels in general. And that covers quite a few of most of our reactor designs now. We covered today the heavy water reactor, the 4th generation reactor concepts, fast breeder reactors, and we can talk about the autonomous reactors. These are also called the battery reactors. This is an idea that satisfies the need in some location in the world for building small reactors, not the 1,000 megawatt electric to produce electricity, but they can produce heat for small community. And one of them is what's called the 4S reactor, super safe, small and simple, 4 S's there. And the idea is to provide heat to a remote location like the city of Galena in Alaska. That city doesn't need a 1,000 megawatt electric reactor. They depend on very expensive diesel fuel to provide them with heat during their long winter. The 4S reactor is designed by the Toshiba company for small applications in remote locations of the world. You could see the reactor here built underground with a heat exchanger and the reactor core in the same type of a pressure vessel. So in that case, it's a liquid metal system, and they don't use any pellet pump. They use an electromagnetic pump that I suggested for liquid metal systems before. The reactor would last for a very long time. It has a very good neutron economy that don't waste their neutrons. So they have basically a core that is raised and lowered in between a reflector. Once they bring in the core down within the reflector, the neutrons reflected back to the core make it critical. So in that case, they don't waste their neutrons into control rods. It's interesting to look at the tech specs or the technical specifications. It's a 30 megawatt thermal reactor only, producing at an efficiency of 1/3, 10 megawatt of electricity. Now, notice the fuel here now, it's a mixture of metallic uranium and plutonium and zirconium. The pumps are not impeller pumps, primary electromagnetic pumps, and the whole thing would be in place underground. So it's a very safe system, and in that case, it can provide a need for remote locations in the world. This is a pilot plant with the intermediate heat exchanger that Toshiba is putting into it. Not to be outdone, in the United States, the National Laboratory came up with their own small seal transportable autonomous reactor. They named it with an acronym SS star. It's a size that is small enough to be possibly carried by a barge or a large truck in place at the location with a steam generator in the same core, used for say 10, 15 years, and then returned back for recycling to where it was generated. The diameter is only 3 meters, as you could see here, with a length of 15 meters, so it can be carried in a truck in general. So in that case, the reactor would be a battery reactor, because simply you do not get it recycled at the site where it is producing power. Some companies in the United States are taking the challenge of the small reactors. One design is called the Hyperion power modules, and it's shown here. It only produces 25 megawatt electric of power. This should be compared to the 1,000 megawatt electric of utility level reactors in general. Notice the coolant here. Oh, it is using a coolant that was suggested in the chapter on Generation 4 reactors. It's a lead bismuth alloy. And the enrichment here, I have been telling that to people that the 3 to 5% enrichment is a really bad idea that was suggested by Admiral Hyman Rickover, and the nuclear industry struck with it, whereas reactors that can, research reactors can be built up to the 20% enrichment. So they're mentioning here the 20% enrichment. They are smart designers in that case. That's they are trying to get it licensed from the Nuclear Regulatory Commission. Not to be outdone, the Europeans also, by a company Urenco that carries the enrichment process in Europe, has come with their own design. So many private companies are suggesting really the building of small reactor. You could see here they're building it underground, and in between the reactor modules, I would have the steam generation modules, and they think that there is a place for it in the nuclear industry. NuScale is another company. One of their vice president is one of our students who took our class. They try to overcome the problem of the decay heat. So they surround the small core, in that case, with a pool of water. If an accident happened, the decay heat would evaporate the water until a level where air cooling would be just enough to keep the system from melting. It is a very small system as compare here to the NuScale, to the large scale one. So the new designs also respond to the need of small systems because of the lack of capital that the utilities can invest into for large systems. Rolls-Royce also came up with a small design. They show a design here. It's not very large, and you could see that the core and the heat steam generator are enclosed in the same containment, even with a pressurizer. So it's a pressurized water type of reactor. So many locations in the world hopefully would be adopting those battery reactors, all small reactor in our future in general. I'll remain in the chat room for any question. Otherwise, the class is dismissed. Thank you for your attention. Anshal, if you have a chance, you should visit the site of the EBR1 after you visit the Yellowstone Park. If there are no questions, thank you, Miguel Valencia, to everybody. Everybody can be dismissed now.